Now that we have the idea that these walls and air, fluids, all these things have thermal resistance or resistance to heat flow and can be modeled as resistors, could we make circuits out of them? Well, yes we could. Let's make a simple circuit that's just a series circuit. Now in your electronics class you probably learned that resistors in series simply add up to one total resistance. Another thing that you probably learned but may have forgotten is that the current flow through all of those resistors is the same. Now that analogy holds in thermal systems as well. So think about this wall as if it's on the right, it's outside, on the left, it's inside your home, and it's winter time, so the wall temperature on the inside is at T1, the air temperature is T sub infinity 1, and then outdoors, the temperature of the outside of the wall is T2, and the temperature of the air far away from the wall is T infinity 2. So there's two bulk temperatures to consider, the bulk temperature inside your home in the air and the bulk temperature outside. Now if you think about what's happening there, you might say, well, what's the heat loss rate? Well, the heat loss rate has to be equal to the heat transfer rate from the air to the inside surface of the wall, from the inside surface of the wall to the outdoors, and then from the outdoors to the outdoor air, assuming that we're talking about a steady state process. So all of those heat flow rates are the same through the air inside the home, through the wall, and then on out to the outdoors. And that just makes sense by analogy, because the current in the electrical circuit can't be created or destroyed. You can't destroy charges, but the or I should say charge is conserved. But in the thermal circuit, energy is conserved. The thermal energy can't be created or destroyed. It's just not changing form, so it simply remains the same amount, and therefore the same, a constant rate has to flow through all of those. Now, it's a little more complicated when you're talking about a home, because it's not just one flat plane, and in fact the thermal energy will spread out in 3 dimensions, typically more in 2 dimensions, but it will spread out, and well, I guess there's a third dimension too. A lot of heat escapes out of your roof. But the point here is that whatever the flow rate is from the air inside the home to the walls is equal to the flow rate of heat through the walls, and is equal to the flow rate of heat from the outside of the walls to the outdoors. And I think the reason that a lot of people struggle with this is because they realize the outdoor temperature of the walls is lower than the indoor temperature, so they feel like, well, it's colder, so heat couldn't transfer as fast. Well, remember that the air outside is colder still. The surface temperature of your home, if you keep it warm, even on the outside, it's at a higher temperature than the surrounding air. It may be difficult to detect, and it may vary along the entire surface, but that's still the case. So the point here is that the heat flow through this resistance network, it's just a series circuit, is exactly as it would be with our electrical analogy. So there's an overall driving force for heat transfer from the difference of the temperature inside the home's air to the temperature of the outdoor air. That's the driving force for heat transfer, just like the electric potential difference across all 3 of the resistors pictured here is the driving force for current through those resistors. Now, if you stop and think about it, each resistor has its own voltage drop, and all of those voltage drops have to add up to the total voltage drop. In the same way, each of our thermal resistances has a temperature drop, and all those temperature drops adds up to the total temperature difference between the indoor air and outdoor air. So the analogy still holds. The only thing we need to do is write the heat transfer rate equation, and when we're talking about air inside the home, that's natural convection, through the wall is conduction, and then outdoors would be convection as well in our simplified model here. So you see that the first term after Q dot is equal to H1A delta T, where we've got the temperature of the air inside the home and the temperature of the wall, T1, as the driving force for heat transfer. That's what drives thermal energy through the air inside of the home to the wall. The next term represents the conduction through the wall and is the same rate as from the air to the wall, and then finally convection in the outdoor air is the final term. And again, these represent each of the resistances and the heat flow rate through each by analogy, the current through each. So we could write this in terms of a total resistance instead, where we use the overall driving force for heat transfer, the ultimate temperature difference between the indoor and outdoor air, and then the resistances are simply the sum of the resistances because they're simply in series. So we've got convective resistance in the indoor air, conductive resistance in the wall, and then convective resistance outdoors. And here's the equation for it. This is where we just plug in things we've learned before about convection and conduction resistance. Now notice that this is not a case where H1 and H2 are the same thing. What would affect those? Well, the air inside of your home is probably relatively still. You're probably not blowing it around much, but outdoors in the wintertime seems like that's when the wind likes to blow, right? So outdoors the convective heat transfer coefficient may be larger than indoors simply because the wind is blowing. Now that doesn't change the heat flow rate from the outdoor wall to the air unless all of it can change. And the way this works, the higher convective heat transfer coefficient will tend to pull thermal energy from the wall quicker, and so the temperature of the outdoor wall will drop, and that will reduce that driving force for heat transfer and thereby reduce the heat transfer rate, so that the heat transfer rate again through the entire circuit is the same. Now there's also something called thermal contact resistance. If you think about a processor in your computer and a heat sink on top of it, where they touch, they're not perfect surfaces, and that's the reason that you use heat sink compound, so that you make up for those little bit of differences, but it's important that you not have it too thick. I got a TV for free on Facebook Marketplace, huge TV, 73 inches, and when I picked it up, he turned it on for me and showed me that it worked in the sense that the controls and all of that worked, and it showed light on the screen, but only a small portion of the picture displayed properly. Most of the picture was either black pixels or white pixels, and the reason is because this was a DLP TV, and it's a technology that was pioneered by Texas Instruments, and it was popular, maybe 10, 15 years ago. But basically, inside of this TV is a really small microchip, essentially, that had really fine mirrors made on it. Now it was just an array of mirrors, and in this particular TV there were over 2 million mirrors because it was just a 1080p TV. So if you do the math, it turns out that's 1,080 lines by, I think it's 1,920 lines, so you do the math, it's over 2 million little bitty mirrors, where one mirror is for each element. Well, it turned out that when I took this thing apart and I took the chip out, I had to take a heat sink off the back. And you could actually turn it over and look at the array of mirrors and see a pattern where you could tell the mirrors were not working properly. And if you turn over to the back, the heat sink compound they had used peeled off and separated very easily from the chip in the very area where the mirrors had failed. It matched exactly, so the messed up pattern on the screen matched exactly the failed heat sink compound on the back of that chip, and that's why it failed. So I ended up buying another chip, put it in, it worked great. Ended up getting rid of it. Some guy wanted it for his man cave, and I decided I didn't really need it. So contact resistance is something that's really important. What it appears like is an extra bit of thermal resistance, and so there's actually a temperature drop between the two surfaces that are supposed to be in intimate contact. Now that contact resistance is relatively small usually, especially if the surfaces are nice and flat, but it can be significant just depending on the application. Another thing I do, I fix things, electronics particularly, just for a hobby, as if I need another hobby. But so I found a TV someone had thrown out. It was an LED TV. It was a decent size. I think it's 55 inches or something. I have it hanging over my fireplace now because I ended up fixing it. Well, what would happen is you would turn it on, and you could tell that it was operational in the sense that the controls and things were working, and the logo would come on the screen, but then the light would shut off and then it would turn on and shut off. So it was flashing. It wasn't a high flash rate. It was every second or so. It was like it was trying to start and couldn't keep going. And so I tried to figure out what was wrong. Finally, I came to the realization that this was a TV that was backlit by light-emitting diodes. And so these light-emitting diodes are the actual source of the light, and then there's a screen that's a liquid crystal display, and it blocks the light when necessary. Well, what had happened is there's several strips of LEDs on the back of the TV, and one of those strips had one LED that was bad. And when I think it was about $15 or so, I replaced that, and the thing came on and worked beautifully. I watch videos on it with my daughter frequently now. And when I put it back together, though, it was a really interesting situation. The light-emitting diodes were mounted on top of a circuit board, but this wasn't just any circuit board. Most circuit boards in electronics are made of I guess it's a fiberglass or phenolic type of material, and they're not very thermally conductive. They're some type of a composite. But these circuit boards were actually made out of aluminum, so they were thin aluminum strips, and you might say, well, that doesn't make any sense because you got to somehow get power to the LED, and the aluminum would just short it out. And you're right, but the way they overcame that is the aluminum bars themselves were coated in a paint, and then the traces for conducting electricity were laid down on top of that. Any vias, which are holes that have electrical conduct going through, turns out they drill and then they coat those as well with this insulating paint. And the purpose of making it out of aluminum is so that heat can flow out of the LED through that aluminum and to the back plane of this TV, which is made out of metal. Well, when I put it all back together, I put a little bit of heat sink compound behind each LED on the aluminum strip, so that when that aluminum strip touched the back of the back of the TV, the LED on front could get its heat through. So I increased the contact between the back side of those boards and the back side of the TV. So just like in your electronics class, you could put resistors end to end and make a series circuit, but you could also put them in parallel and allow current to flow through both at the same time. And depending on how large the resistors were in terms of their resistance value, a differing amount of current would flow through each one. We can set up a thermal network in the same way. Now look at the sandwich on the screen. It's made of two different materials that have thermal conductivities K1 and K2. Now, one thing that students get wrong here is they immediately see the sandwich and they think heat flow is vertical, and it's not in this case. It's only horizontal. As a matter of fact, we'll only be able to deal with single direction heat transfer in what we learn here today. Multi-direction heat transfer becomes very complicated very quickly, and actually multi-direction current flow becomes complicated very quickly. I have had the opportunity to work with multi-direction current flow in my career, but for now we've got insulation on the top and bottom, and so we've got a different temperature on the left side, T1, as we have on the right side, T2, and heat is flowing, say, from left to right, just to keep the analogy going with the circuit below. So T1 is a higher temperature, T2 is a lower temperature, and the effective resistance of resistor 1, that material that's at the top with K1, is simply what we had before, right, where we have the essentially the cross-sectional area and the thermal conductivity, as well as the thickness of it, the length that the heat has to travel. Has all of those in a form of, what is it, L over Ka, something like that. And so each of these two resistors would have different amounts of thermal resistance, not only because of their thermal conductivity, but because they have different flow areas, A1 and A2. Now they both have the same length, so that dimension would be the same. But still, they would have different resistances. Well, this can be modeled just like two electrical resistors that are in parallel with each other. As a matter of fact, the total resistance of this network is the same as the resistance of two electrical resistors that are in parallel, where you have 1 over R total equals 1 over R1 plus 1 over R2. And when you rearrange and solve for R total, you see it there on the right as the product of the resistances divided by the sum of the resistances. Now there is an example about this on page 405, 407. I would ask you to go through it. I'm not going to go through it. It is a very good example, and there's some good points made in it that you need to know.